Hello everyone, my name is Paul James and I'm here to present our project Uganda Computer Graphics Based Diagnostic and Skincare Simulation Platform. My colleague is Songo Julian Paul and yeah, let me begin by explaining the keywords as we can see them. Our first keyword is 3D face modeling. 3D face modeling is getting uh, a realistic view of an actual image, let me say the face of a human being, into something that a computer brings out in a realistic way. And computer graphics, well, when we understand computer graphics are visual ways of communications using computers. And when we talk of visual programming, it is just a series of blocks that follows to perform a given task. And as we can see, these are examples of the blocks that we can talk of when we talk of visual programming. And then explainable AI. Explainable AI is just explaining something that has been extracted from the image, that feature, into something that a human being can actually understand. As we can see here, we are seeing the GradCam, and then we are seeing the actual image of a condition which has been uh, extracted and actually visualized using the GradCam, as we can see the image. And then we also talk of generative adversarial networks. Here, this is whereby we use the fakes and the real images. So we use the real image to extract the fake image out of it, and then we compare, and then later it is all taken into what we call a dis discriminator, and then it judges which images are real or fake. Well, related work. I reviewed 10 related words, but I'm just going to explain for you a few, like Video XL, which is the extract long videos, vision language model for our scale video. This one actually brought about a technology or a terminology called the visual summarization token, which is supposed to summarize a clip of a video, and it gives you the accurate results of it, as we can see. And they use Gwen 2, which is the 7B LLM, and then the clip VITL encoder, and it introduces, of course, the one I already talked about. So the challenge here was to overcome the bottleneck of limited context length and substantial computational and memory costs, which prevents MLMs from effectively processing extra long power videos without significant loss of the fine grained visual information. And then now the limitations. Here, the provided source, of course, within this, the provided source never had any limitations. And then when we talk of another one, we talk of Calico, which is it focuses on the semantic cost segmentation, and it introduces the novel task of path focus semantic cost segmentation. The goal is to overcome the limitations of existing large vision models out there which struggle with segmentation and reasoning across multiple images at the fine grain object part level, which is like, for example, identifying, segmenting, and labeling common and unique parts. And the limitations, it also had no limitations as for the paper. And then we go to develop, which is the generating the 3D air from a single image using diffuse models. And then it is to instantly generate the detailed 3D air uh, geometry from a large image, uh, circumventing the need for low dimensional intermediate representations like guide stands used by the previous method. So here the limitations, first of all, it lacked, let me say, the synthetic data set used for training, despite its site lacks hairstyles involving braids and then accessories, ponytails, and bands. So the framework also prioritizes local air details over perfect image alignments. That means there are some images which we will upload and will not get the air structure well. Yeah. Anyways, what is our problem statement? We have two, which is the domain application problem and the computational problem. Our domain application problem is the healthcare inequality in dermatological care. When we talk of healthcare inequality here, is that outside there, we have, okay, let us say in Uganda, we have over 25 dermatologists, which is serving a total population of 45 million people. And by the recent research, they are over every year. That population of Uganda suffers it is said is 60 to 70% of the skin conditions. And looking at the dermatologists available, it cannot work on that available population effectively. And then there is a bias in global AI systems against darker skin tones. We have seen that if they are existing systems, then they have used uh, white people's skin data set, which is not favorable for the colored, let me say the darker skin tones. And it usually leads to misdiagnosis, and in most cases, it doesn't work at all. So, and then the computational problem, we have real-time skin condition simulation and diverse tones. And that is one thing that we want to work on. And then integration of diagnostic AI with 3D graphics. The graphics here is, first of all, we are going to use the 3D graphics to just extract the features, and then, of course, for privacy purposes, when an individual takes a pic or uploads a pic, the pic is just analyzed, and then the feature is extracted from it, and the pic is immediately deleted. So we cannot see the picture, and even the people controlling the systems will not see the picture, but they will see only the uh, extracted visual back and analyzed of the existing condition. And then there's mobile optimization for low resources. We want to make it to be used for as low as small devices are concerned. And the research questions and objectives. We had a lot of research questions and objectives, of which a few of this I will mention here. Like, for example, what AI can models overcome inherent biases derived from global data sets to provide accurate diagnosis for African populations. And then here the objective is to develop and train a robust diagnostic model for Uganda skin condition. And as we can see, among other objectives is to develop a high fidelity skin condition simulation pipeline, and then to also engineer an interactive and accessible web-based platform, among others. And research contributions and outcomes. First of all, we develop a skin diagnosis system based on the CLIP model that achieves 72% accuracy and F1 score of 0.71, which is literally 72%, cost is 0.716 something. We train and develop a segmentation model based on the UNet architecture, and then we build an explainable AI module for producing broadcom heat maps to visualize the regions influencing diagnostic decisions, providing transparency and building user trust. And we made a photorealistic visualization system tailored for African skin tones on a web-based prototype. And methodology. Here, we in our methodology or the system architecture, we are going to allow the user to input the image, and then the AI will do its diagnostic pipeline, whereby it will use the visual visual transformer to extract, or okay, to classify the image, that if this image actually belongs to this, and it will also give its own percentage, or let me say probabilities at which it is classifying that uh, thing. And then on top of that, now it is going to use a large vision transformer like clip or segment anything to extract the affected area, and then that affected area is what is going to be mapped into the avatar, and finally it will be visualized to the end user in the user interface. And plus it follows the diagnostic plus the confidence score, and then the affected region areas. And now this is the Florence 2 architecture, which is another model that we train also. We can see here that we use the standard multi-head self attention, and it enables the rich contextual feature extraction from the images, as we can see. And then there is a hierarchical, it uses what we call a hierarchical multi-scale vision transformer, which is all the same as visual transformer, to capture both global structure and fine-grained details across scales. And then our training algorithm was transferring learning from ImageNet, which is the pre-trained weights, and then GradCam used to make predictions interpretable, and others follow. And then we also train Gwen 2.5 VL, which uses a multimodal transformer with cross attention to fuse image plus text features. And although we trained this one here, it wasn't giving us the perfect score that we actually desire or we expected, but we had to uh, put it because it was actually promising. And these are mathematical tables, which okay, let us say mathematical objectives, which uses the multimodal instructions tuning with a standard cross entropy loss. And then we can see here that this one possesses what we call a visual encoder and projection plus a language model, of which now here takes the language instructions and the response will be in the text language form. And then we come to clip. Now clip on this clip trains using a contrastive loss that aligns image and text embeddings, and then it encourages match image text parts to be close and mismatch pairs to be far apart, as we can see here. And then this is the clip, still the mathematical format, and then the deployment part. And our dataset description and exploratory data analysis, we talked of using number of images were actually over 2000, and resolution was, as we can see. And then we analyze it and visualize it, of course. We want to understand what kind of data set we are using here, and we can see that the average image property by condition, we have 7 conditions that we are working on so far, and all the 7 conditions we can see uh, according to their average image properties, how they are basing on the width, height, and file size plus the megapixels. And then the same thing here applies, only that this one is the skin condition distribution bar graph. So it is going to tell us the number of images available in each and everything, and that is the images that we use, with the highest being uh, the ringworm, because the having the highest number of images. Also, although when we were training these things, it wasn't recognizing the ringworms. Like, let me say, it was mistaking the ringworms to be uh, Hakini and the Rosacea photos, images diseases or something like that. And then also we can see down here that we have image width versus height scatter plot, and we can clearly see how it has been visualized. And output results and discussions, sorry. Here we have seen the clip results, the accuracy test, which is above 70, and then the loss. And when on the other hand, it wasn't as we expected. The training loss and the validation loss are not as we seem to see them. And then the unit training, the progress, we are seeing that we have the average dies, which is over, of course, 90, and then the loss being below. And then This is our table showing the results of the models that we have trained so far and how they have and their score, let us say, basing, of which our best was the UNet. And UNet in this hand we incorporated with the large vision model like segment anything and explainable AI results and discussions. Still, we are talking of how AI is going to explain this one here, and we can see it from this confusion matrix that just talking of one of them here, cinema photos. When we come to it, it recognizes that 156 photos were classified under cinema, which is actually a good prediction in this case because when we look at some things which were not classified under it, there were actually many. Okay, and the global feature extraction, this is all about explainable AI, and then the model selections and deployment. We selected clip, of course, and then the balance, performance, moderation, everything that we are seeing here, the reason why we did that. And then we are going to deploy our pipeline, as we can see. So now this is our deployment and then the UI, as we can see. We have uploaded, and without any doubt, we are able to understand that the results can also be given in Luganda depending of the language which you change, and it is a good thing so far. Then it is visualizing from the image here that this is the affected area. It is just going to extract those ones and puts them where it is, or let me say, the largely visual features from the image that has been extracted, and that is what it will put uh, on the image. So mm, now we have limitations. Like for example, large model size for pre-training were actually hard to get, and then annotation of dataset for segmentation was another hard thing, which almost took a full day to 24 hours to annotate the entire dataset of over 5,000 images. And then the large model generalization on small dataset segmentation, and then there's limited access to cloud compute uh, resources, and then long duration of training experimentations that limit further investigations and variations, hardware limitations uh, when training large vision models, and then in conclusion, to further improve the system, of course, or expand, we need to expand the dataset to support more reliable fine-tuning and generalization, and then optimize models using lighter architectures or knowledge distillation to reduce resource usage, and then also enhance visual programming tools to let users uh, interactively adjust simulation parameters for personalized treatment planning. And then another thing, we are also going to integrate real-time telemedic graphics to support ongoing monitoring and visualization of context. And something that we have actually done is that after you training your uh, let me say, after you testing your results and the results have been forwarded to you, you can share. That is another feature. You can share these results to your nearby doctor, because under it, it is going to tell you that these are AI results and the AI results are not uh, to be trusted. Therefore, you should consult your doctor, and that is why there is a sharing button whereby you need to share your results to your doctor. Yeah, and these are references. And then in acknowledgement, we would like to acknowledge Mr. Galwanga Marvin because he's the root and is the one who made us understand all about graphics being used in the large vision way and using vision transformers among other models. And yeah, at least we should appreciate him for the great thing that made us understand how to apply graphics from the normal way to the vision way. So we would also like to extend our gratitude to all technical papers and to the people who wrote all those technical papers that we cited, and then all the platforms uh, like Cargo, Collab, Hanging Face, Harzix, and Docker Hub. There are many which we can mention here. Thank you. I remain apologized.